אנחנו מתחילים. So first part, the exam issue is kind of complicated because I'm traveling right after your. On the 5th of March, I'm already flying away. So, and I just was trying to figure out with Neely if there is a way she can actually scan the exams from me. But if not, or if it's impossible for me to check them while I'm away, it's going to be a lot easier to have a multiple choice exam, of course, for all of us. But and since there are also people here who, several of you cannot be at the 4th of March or cannot be before or after, I don't know what, so it will be easier anyway to have it as a multiple choice exam, and this will be a lot more flexible for me also to do it when I'm not around. So as far as I'm concerned, unless you really scream, it's going to be a multiple choice exam. Now, you can see the exams from last year if you want to see how it looks. If not, I'll send them to you if Neely doesn't have them, just to have an idea what you're talking about. So essentially it's something like 20 questions or something. Each has essentially 4 options, and some of them are easier than others of course, but you have to do all of them, so it doesn't matter. And they all have equal number of points. Okay, so by the way, I'm teaching today. Ravid will come again hopefully on Wednesday, but I think he actually sent you some exercises, so you're not supposed to be without work. Anyway, so we still talk about data compression in general. And we started to talk about the notion of a code. And I just want to remind some of the basic definitions. So we have some sort of a variable, random variable, which has some probability distribution, which may or may not be finite, discrete, or continuous. At this point, I'm still thinking just for simplicity about discrete variables, which can take essentially some countable number of options or values, and we want a code. So I want to code them by what I call the code words. So every value of the variable will be assigned some sort of a string in some alphabet, which I usually denoted by sigma star, which means all the finite strings over some alphabet. So this alphabet can be, this alphabet is some sort of a letters A1 to AK or AD. D in this case is the size of the alphabet. And so this can be like, A, B, C, D up to 26 in the English alphabet, or in the Latin alphabet, or 0, 1 for a binary alphabet, or 1, 2, 3 for a trinary alphabet, or A, B, C, or for the 4 codons of the DNA, or whatever the 21 proteins of the there are 20 or 21 amino acids that encode proteins. There are many different ways of thinking about it. So we have finite alphabet, so cardinality of the alphabet is this dimension of the alphabet. And without loss of generality, we will assume the binary alphabet, which is just 0, 1. It's generally enough because I can encode any other alphabet by finite strings of 0, 1s in many ways. Okay. So we, unless said otherwise, this is what we call the binary code. And these are often called bits, though they're the meaning is slightly different than the bit of information which I already mentioned, but it's going to be, of course, related to each other. These are just the symbols, 0, 1, or yes, no. Okay, so this can be, you know, spikes. In some sense, I can think about binary codes. In some spike in some interval, let's say 1 millisecond, 10 milliseconds, and then I think about spike train as a sequence of bits, but that's not a very useful way of thinking about spikes, by the way. So there are many ways of thinking about codes, but so the map to this, these are finite strings over this alphabet. So sometimes we just call this sigma. These are finite strings over A. Okay? Any questions about it? So a code word is a map from the variable to the string. And what we usually call the length of the code, it's actually the length of the code word. This is actually some sort of kind of user notation. But the length of the code word for a particular code is the length of this string. So this is length of the strings. Okay? So this is an ordered string, and so the length is how many symbols are there. That's as simple as it sounds. Okay? And then we said that a code is non-singular if this map is unique in a sense that, so this is always a function. It maps variables or the values of the variable to strings. But if it's non-singular, if Cx is 1 to 1. It's also invertible. So I can, for every object there is a unique string. Okay. Otherwise, I don't know what I'm calling. I'm immediately collapsing my code. Okay. So this is non-singular. And then we said something much more interesting. So the idea is really not to encode one value of the variable, but to encode a sequence, or what we call extension of the code. So in some sense, we want to encode a sequence, x1, x2, and so on, some finite sequence of size n. So the simple extension of the code of the sequence is going to be the concatenation of the codes. Okay? So we want it to be a string, and the simplest possible way, it's not by the way the way we usually want to do it. We actually want to do better than that. So this is simply going to be a concatenation of the code words. So it's a longer string that encodes all of them, and this is simply concatenation. Which means just writing the code word one after the other as one long string. Okay? And then we define something which we call so this was a definition. Everything here is definition essentially. The code function, this is called the length function. So the length function is essentially a map from the code, the variable of the values of the variable to the integer numbers. I mean the length of the string. Okay. So and then we said that a code. So this is a definition here again. A code is uniquely decodable. Uniquely decodable if any extension, I mean for any n, any length n, is also uniquely decodable, is non-singular. Okay? Which means that the concatenation of the code is also one-to-one. Okay? Is this clear? Yeah. And then we ask ourselves, okay, when is the code uniquely decodable? So I gave you some example where it's non-singular but not uniquely decodable. because the concatenation is not going to be uniquely parsed. But another way of saying it is that there is a unique parsing into any string. Yeah, so unique parsing means that I can parse it by putting commas, essentially. So if I go through a string, I can parse it into the code words. And so there may be, by the way, strings which are not parsable in the sense that there are things which are not code words there. But if it is parsed, if I can parse it, it's uniquely parsed. They're not two different parsing. Okay. So for example, we look at our language. The text in our language is usually, it's neither uniquely decodable nor uniquely parsed. But if you put spaces or punctuations in the text, up to the fact that some words are not don't have unique meaning, that's a different story. So it's not one value of the variable, but this is the basic intuition here. I mean, so think about our language as something which is parsable into unique sequence of words or unique sequence of sentences or whatever. Natural languages are not that regular, not that well behaved, but that's a different story. Okay, so and then there was a question. Okay, so when is the code? Is there any simple condition on the code to be uniquely decodable? And I stated that I didn't prove it. So there is a theorem, which is usually known as Kraft Inequality. Sometimes called Kraft-Macmillan Inequality. I don't know. There are many people, all the same names appear in the game. But this is the most common name for that, which is code C of x is uniquely decodable. Let me just write it like this. Uniquely decodable if and only if its length function L of x obeys this the sum of all possible L6 of the dimension of the alphabet, the d of the alphabet to the minus Lx is less than 1, less or equal 1. Now this looks like a very surprising thing, because nothing else in the code matters, only the length function. So in principle, you would imagine that I could have all sorts of problems with that. So if the length function obeys that, then I can for a given code, the code is uniquely decodable, and if it doesn't obey that, if there is, for some instance, if there is a length function that obeys that, I can build the code with this length function, which is uniquely decodable. Sounds strange because, okay. Sorry? No, sounds like a good question. No, so there's something tricky here if you think about it, but no, I don't need to assume anything. So I'm going to prove it. Before I prove it, so we talked about some special cases of codes, what I call the prefix code or the suffix code. It's essentially the same thing, just invertible. So a prefix code, so it's enough to speak about just one of them. A prefix code is a code where the code, no code word is a prefix of another code word. So, for example, it's the kind of thing we see in language all the time, where sub-word is also a word in the language, substring of the word, and this is not allowed in a prefix code. Okay? So we talked about prefix-free, actually, prefix-free codes, or similarly suffix-free code. And we said that so I don't want to repeat the definition, but these codes can always be described by a tree. So if for the case of, let's say, binary tree, so any binary tree where I interpret the branches as letters of my alphabet in some systematic way. So left is 0, right is 1, or something like this. So any tree like this where I interpret the code words as leaves of the tree, by the way, not necessarily all the leaves, but some leaves of the tree, and this is the root. So any code word is a path from the root to the leaf. This is uniquely defined, and these code words are always prefix free, because I cannot have two leaves along the same. The leaves are by definition the ends of the tree, the end nodes of the tree. So this is a code word 0, 1, 0, 0, and this is a code word 1, 1, 1, and so on. If I don't use this leaf, for example, for a code word, it's okay. So 1, 1 is not a code word. Okay? So if you have a tree and you put your symbols, your object X on the leaves of the tree, you always get a prefix code. And if you interpret it in reverse, it's a suffix code.
Does all the prefix tree codes? Trees are.
So all the prefix tree codes can be written as a tree. Yeah, that's it's a very simple proof. Yeah. If it's prefix tree, then nothing. I can just write the code word as one path from the root. Okay, so for prefix tree codes, they are obviously uniquely decodable. And actually, you're going to show in an exercise, I don't want to show it here, and that if they're prefix D, they obey the Kraft inequality directly, just by counting length on the tree. So the length, in this case, the length function is are those numbers 2, 2. And 1, 4, 4, and 3. Oh, 4, 4, and 3. Okay, no, not necessarily in the right order, but never mind. So these are all the lengths of code words in my tree. Okay? And this one I eliminate it. It's not a code word. Okay, it doesn't matter. Okay, so you can easily convince yourself, and I want you to do it yourself. These numbers obey the Kraft inequality with d equal 2. Okay? So before I go to the more general proof, which is actually quite elegant in a sense. So this sounds a little, how do I prove that any length function can have a uniquely decodable code behind it, which if and only if it obeys the length the Kraft inequality. So this sounds, by the way, the Kraft inequality is true not only for things like code words. I mean, they're true for essentially any encoding of objects in the world. I mean, for example, computer programs are uniquely decodable code in some sense. Because, okay, they are finite strings over some alphabet. I mean, that's after the compilation. Never mind. So eventually, a program is a code, which runs a Turing machine or something like this in the background. And so all the codes, all the programs which are essentially encoding some sort of variable, they form a uniquely decodable code. So they obey the Kraft inequality and so on. So actually the Kraft inequality should be obeyed for many, many things which you don't originally or initially think about them as codes, but they are codes. So if they're uniquely decodable, their representation in some strings must obey this the Kraft inequality. Now,
but the Kraft inequality is only for one direction. It's only if it obeys the inequality, then it's decodable. Or
so actually, you have to interpret the other direction correctly. So for any code function which obeys the Kraft inequality, there exists a code. There exists a uniquely decodable code. Not necessarily one. Maybe many with the same length function. For example, if I have a prefix code, the suffix code and the mirror image of it is also obeys the same Kraft inequality.
Can you maybe phrase it formally?
Yeah. So when I said if and only if, I have to be a little more careful. So if it's uniquely decodable code, then its length function obeys the Kraft inequality. If there is a length function which obeys the Kraft inequality, I can find a uniquely decodable code. with this length function.
But what is the length?
So the length function is any function that obeys this. Any.
But you defined it through C, through the.
No. So the if and only if here is a bit tricky. I have to specify it more carefully. If C is a uniquely decodable code, then it has a length function, and its length function must obey the Kraft inequality. Now, if you give me a length function which obeys the Kraft inequality, I can find at least one uniquely decodable code with this length function.
But what take length function which is always infinite?
No, this is not. I'm talking about finite strings. Okay. Finite strings. Not all of them are finite. It can be an infinite sequence of. I mean, the sum here can be of infinite size, of a countable size. But these are all finite strings. So the L function is the L is a function from x to the positive integers, finite strings of positive integers.
Ln function.
Yeah. So L length function is any function that from the values of x to the integers, finite integers without infinity, and it obeys the Kraft inequality if this function obeys this. Okay. So the if and only if, you're right. There's something I wasn't very accurate here. If C is a uniquely decodable code, then its length function obeys this. And the other way is actually easier. If you have an L function, a length function which obeys the Kraft inequality, then I can find even a prefix code which obeys with this, simply by putting it on a tree. So there are many codes. It's not a unique code. So the Kraft inequality doesn't uniquely define the code, but any uniquely decodable code obeys the Kraft inequality, and any sequence of lengths which obeys the Kraft inequality correspond to some uniquely decodable code. The if and only if is not with respect to it's not a unique code. There are many codes. For example, I can put a prefix code with this length function. So I can always build a tree where the lengths of the leaves, the trajectories from the root to the leaves, are the length function that you give me. If and only if they obey the Kraft inequality. Okay? So that's not obvious. This is one direction. At least was a surprise when I heard it first. So what is it? What is the proof of the theorem? So as I said, I mean, you are going to prove in your exercise. I'm giving you to prove it directly for trees. Just construct. It's a very simple construction. You just extend the tree all the way to the end, and then do some counting argument. And you get it immediately the equality. By the way, okay, but so I'm going to give you a proof, which is so I'm going to prove of Kraft inequality, and this proof is actually due to a very smart mathematician called Karush from the 50s. But he actually had a series of very surprising general proofs of things in information theory. Okay, so what is the idea? So if you're having an extension, so let's say CK is an extension of K symbols. If a code of K symbols. So let's say, okay, so CK is a sum that just denote it, the extension. So essentially, if I have an extension by concatenation, so I have, let's say, CX1 up to CXK. This is my concatenation of the code word. So this is going to be L of X1. The length of this CK of this particular sequence is going to be L of X1 plus L of X2 plus L of XK. Okay, so again, it's a kind of abusive notation. But this is the length of this code words plus the length of the second code word. So the length of the extension is simply the sum of the length. That's by definition of extension. Okay, because I just put them one after the other. Okay. So the length function in this case is L. So this is and this is if this extension is a concatenation. Okay. So so now let's look at the following thing, which is the sum of d to the minus Lx over all the x's. So this is the thing that I want to prove, which is bounded by 1.
X is a sequence of singles, or is it a single?
No, now it's a single. So x is belongs to the single code, single letter code, not single letter code, single x. Okay, so this is not an extension yet. I'm just taking one value of x. So this is what the Kraft inequality wanted us to show. So the statement in the Kraft inequality is that this is for the symbols themselves, for x in x. Yeah. Okay. So it's not yet the extension. So I'm looking at that x in x, and I look at it to the power, to the nth power. Okay. So what do I want to show about it? So this is a sum to a power. So what do you know about sums of powers of sums? So this is equal to the sum. Yeah, I want it to n of 2k. Make sure that I'm using I'm not going to confuse myself. I wrote k, so let's put k. So this is what is it? So essentially, when you sum a product of sum, essentially what you get is d to the L1 plus d to the L2 and so on for all the possible things. And then you get k times. Every time I have to choose one of the x's in the sum in the product. So it's a sum over all the x's x1 to xk, all the possible when every one of these I is in my alphabet. So it's the sum of k times this sum of what? Of d to the minus L of x1 times d to the minus L of x2 and so on up to d to the minus L of xk. Okay, let me just put it in the center so you see. The camera sees it. Okay, so this is simply opening the power such that what? Such that so I take exactly k of them. So there are k terms. Each time there are exactly k. I pick one from the first bracket and then one from the second bracket, and I simply sum over all those combinations. Okay, so this is what I mean by k's power. Okay. So this is the k's power of this sum.
All the permutations.
Every order appears there. So I pick the first one, and one with all permutations, all the possible ordering, all the, in this case, cardinality of x to the k to the cardinality of x. It's no, x to the cardinality of k, x to the k. So if x is finite, this is a finite sum. At this point, just for simplicity, think about x as finite to make it easier to think about it. So there are, let's say, 10 x's. So there are k out of those 10 in each term. Okay, and they can repeat themselves. Okay, but what is this? This is simply, this product is d to the, so it's a sum. Let's just break this sum somehow. And so I want to sum it in a slightly different order. So this order is over all the possible combinations, but they have different lengths. Okay, I mean some codes are short, some codes are long. So let's say I have so I want to group these terms in another way according to the length of the code. So first of all, what I have here is d of lx1 minus lx1 plus lx2, and so on up to LXK. Okay, so this is just, but this is what? This is the code of an extension. This is the code length, this is what I said here. So this sum in the exponent is exactly the code length of the extension of the code, of the concatenation of the code of x1 and so on, in this particular choice.
But only for concatenation.
Yeah, only for, I'm talking about concatenation all the time. So, so this is the length of an extension, of a very particular extension. And let's say that this has a code length n. So n in this case is simply the sum of the length of a particular extension. That's why I kept n aside for a second. Yes.
K is the number of letters in the group.
So I take a particular k.
But then you also wrote that you need the sigma.
Yeah.
X1 to X3, so it looks like it's the number of letters in the alphabet. So.
No. So I'm saying that this is for all the possible x1 and xk, where each one of them is in my.
Some of the letters alphabet, right?
No, it's not the alphabet. It's the values of the variable x. The letters of the alphabet are the codes, the sequences.
But they are not necessarily.
Yeah, it's a bit confusing because we sometimes call this alphabet. This is not an alphabet. This is the values of x. Okay, x is the variable which has some values, some x that it takes.
No, but you chose the power the same as the length of the word.
No. I'm taking, this is some length, okay? Each one of this LXI has some NI, okay, whatever, some length, okay? Now, this is the sum of all possible letters, all possible values of x.
But it's not necessarily K, right?
Not necessarily, the K is only in the power.
Yes, but you also wrote it there. It's the only. You wrote from XY to XK. So
Yes, because now I'm taking K, a product of K terms.
No, but in the left you chose the same case. So it was in purpose.
the length of the sequence.
Yeah, I wrote it for purpose, exactly for that. So the length of this concatenation is what I now call n. Okay, it's not k, it's n, some number, which is simply n of x1 plus n of l of x1 plus l of x2 and so on in this particular product. There are all possible products there, but for each one of them there is a length. Okay. Now this length can go. So now I want to break this sum into according to this length. So the length can go from what? From k times L min. So let's say that, just for simplicity, L min is the minimum over all x of Lx, and L max is the maximum. So now I assume that x is finite. Then we extend it, okay? So there is a maximum code length and a minimum code length, okay? So L max is the minimum length, and L min is the maximum. So what is the value of this exponent? What is the minimum value? N times L min, okay? So this n goes from let's say L min or k times L min, k L min, up to k L max. Okay? So these are all the possible values that this n can take. This is clear. This is the only trick here. Once you understand this, everything's clear. So I simply break this sum. Instead of according to all the combination of the letters, I break it according to the length of the concatenation. And the length of concatenation can be, the smallest that it can be is k times the shortest word, and the longest it can be is k times the longest word. Okay? Now, there's something missing here. So what is missing here is the number of times that this n can occur. Okay? In my concatenation. So let's just write it, give it a name, call it A of n. So essentially what I did here is taking this power of k, write it like this, and then notice that what I get here is the sum of the length in the exponent. And then, okay, but this sum of lengths is an integer number that is bounded between two extremes. K times the minimum code length and K times the maximum code length. Okay? So the only thing I have to do now is I have to tell you what each of these code lengths can appear more than once or zero. It may not appear at all. It may appear many times. For example, if all the code words are equal size, then this sum L min equals L max, and there is only one length here, and this is then these are all the possible concatenations. But if the length is of different lengths, then some may appear and some may not appear. Okay. So what is an here? So an is the number of times the number of terms in the sums with length n. Exactly n. So this sum has many terms. I group them together if they have the same length. Group them together by counting them an times. An times can be 0, 1, up to whatever, up to at most k, l, k. Okay, I don't know. Yeah, can be many numbers. Okay, now comes the important observation.
If there is a term with length n, then there is only one term length. And in the sum, then
If they have only one length, then there's only one term in this sum.
yes.
And all the others are zero in some sense.
So how can there be many such?
No, so some lengths may appear, some lengths may appear more than one, some lengths may not appear at all. I don't understand. So there are lengths here. Now I don't know the code, so the total, the number that this can take, I only have bounds on it. I know that the minimum one is k L min, which certainly appears, because then I have exactly L min times k, and k, which is k times L min, which is, so then this is the minimum n. And the maximum one, if all of them are encoded by the maximum length, and then I have k L max. Okay?
What do you say about the sum of an?
No, I'm not going to talk about the sum of an. I'm saying that this is this. This is just rewriting it in a different order. Okay?
Sum of an has some kind of...
Okay, yeah, let me continue. I mean, this is not the end of the proof yet. So now I have to say something about an. So notice that maximum number of code words of size of length n bits, of n b's. What is the maximum number of sequences of which? So this is a sequence of the symbols of my alphabet of length n. Okay, so what is the maximum number?
N to the power of d?
Yeah, d to the power of n. Okay, so the maximum number of sequences, or the number of sequences of sequences of length n in d letters is what is d to the n. Okay. So if d is 2, it's 2 to the n. Yeah. If d is 26, it's 26 to the n, and so on. Okay. Simply you choose the first letter, the second letter, in each part of it we have d options. So it's d times this times d, n times. Okay. So this is d to the n. So in order for my code to be uniquely decodable, each one of these sequences is different. Yeah, this is clear. Because the order. So each one of the terms here is a different sequence, a different concatenation. Okay, so now I want my code to be uniquely decodable in the extension, which means that I can decode from the sequence a unique sequence of the original symbols. So which means that the number of objects that have exactly n size, of sequences that have exactly n size code must be less than d to the n. Otherwise, there's some version of the pigeonhole principle. Otherwise, there are two pigeons in one hole, which I cannot decode. So I know, so this means that uniquely decodable implies that an must be less or equal to d to the n. Okay? Otherwise, I cannot decode. So this is really the crucial point of the proof. I simply count. I mean, how many since these are all different sequences, because no sequence, they may, up to a permutation, they may not, but since this, I count about this specific order, so this is a unique extension, a unique sequence, x1, x2, and so on. It's unique. Therefore, I need a unique code for it. If I need a unique code for it, the number of sequences with this length cannot exceed the number of possible sequences. Okay, so this is the condition of uniquely decodable. Uniquely decodable. I want to emphasize it. Okay. So this is critical. Okay, so if this is true, then I can bound this for a uniquely decodable code by this sum, where n goes from k L min to k L max, and this is bounded by d to the n. So this is d to the n multiplied by d to the minus n. Okay? But what is d to the n multiplied by d to the minus n? Is 1. So this is simply a sum of ones. Okay? So it's bounded by what? The maximum term times n. The maximum terms. So the number of terms here is KL min up to KL max. So this is bounded by KL max. That's it. It's enough. Let's say this is 1. This is 0. So this is bounded by KL max. Okay? You see what I wrote there? Yeah. The most important part. I write it bigger, KL max. Because this is 1, and the sum of 1s is at most the number of terms here, and the number of terms is at most L max, KL max. Okay? So this is bounded by KL max. And I use the fact that it's uniquely decodable right here, when I say that AN is less than this. Okay? Okay, but now I'm almost done, because what I get is that a function which is exponential in k is bounded by something which is linear in k. So I started with something which is some constant which is to the power of k, and I proved that it's uniquely decodable. If it's uniquely decodable, it's an if and only if, by the way, with this argument. Then it is bounded by a linear function of k. Now, something this looks like c to the k, which is bounded by some c1 to k. What is this c? So this c must be less than 1. This is true for all k. Yeah? So if this c is greater than 1, then the exponent is going to win the linear function. Well, no matter what c1 and c are. So any exponent, if it's greater than 1, it's going to. So this implies that this constant c must be less than 1. Okay, so this is proved what I just wanted. So I get from this that this constant c was this sum. Okay. So this is a very nice proof in the sense that I didn't assume anything about the code. Not prefix, not suffix, nothing. The only thing I assume is that it's uniquely decodable. And I'm out of my first hour. Okay, never mind. So that's the proof of Kraft. What I really want to emphasize here is how general it is. It doesn't have to be trees, it doesn't have to be anything. Now, notice the if and only if. So if this is true, if it's uniquely decodable, this must hold. And if this holds, then I can use, I have enough holes in my pigeonhole and to put all my pigeons in different holes, which means I have a uniquely decodable code. Okay, so that's the if and only if part. Okay. So let me emphasize one thing about, so this by the way, if you look at the tree, so as I say, the tree must obey it, and the proof is something I want you to do yourself. But when is there an equality in the Kraft inequality? Yeah, in some sense where I'm not wasting leaves in my tree. That's right. So this is what we call an efficient code. An efficient code is when I'm actually using all the sequences, which means that I can actually parse any sequence uniquely, and there are no places where I don't know what to do.
Does it mean that the number of possible x has to be d to the power of something? Or
No, so it can be bounded. I mean, you see in this tree, for example, I don't have all the parts. Okay, so let's just talk about. So, for example, this is an efficient code. I mean, 0, 1. If I have 4 objects, let's say, like my A, B, C, and D. So this is A, B, C, D. So this is a code of size 4. It has 4 letters, and I know that it obeys the Kraft inequality. Actually, inequalities. So this is 1, 2, 3, and 3. Okay? So let's see. It has 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 3 plus 2 to the minus 3. So you see immediately this is 1. So let's see. Half plus quarter plus 1/8 plus 1/8. Now we all see that this is 1. Okay? So indeed, if I sum over the length of the code in a tree, and there are no holes, there must be 1. So this is almost the proof that you want to show in your exercise. I don't want to continue from here. So you see that the tree is automatically obeying this with equality. Now if, for example, I was not using this one, so it's still a uniquely decodable code, but then I'm missing one of the elements here, and this will be less than 1. But it will still be a uniquely decodable code. Okay? So uniquely decodable code as such as correspond to trees. I can always find a prefix code, which is, if it's inequality, if it's an efficient code, then all the leaves of my tree are used. Okay? So in the next hour, we're going to talk about the connection between efficient uniquely decodable code and entropy, and or what we call the first Shannon, the first coding theorem. And then, if I have time, I'll show you some algorithms. For example, the Huffman algorithm, finding it. So that's the next hour. זה עוד פעם על סכום המקסימלי, על האורך המקסימלי של הסכום, ולראות שכל אחד נתון אלה.
נגיד, דיוטיות, נכון? כן. דיוטיות. נכון. זה לפי משפט, בסכום הסכום על
כל האיברים של השפה, כל המילים. זה לא אותיות, כל המילים. כל האובייקטים של X. X
למה זה הולך?
לקחתי חזקה K.
זה 2 ו-1. אז צריך להיות סכום על סכום, נכון? שתי השורות האלה.
אני K קובע. אז אני אומר, מה יש פה? יש פה D to the minus L ועוד D to the minus N של X2.
בוא נגיד ש-K הוא 2.
כן, אוקיי, 2. ואני עכשיו תחל את זה חזקה K. בוא נפלט את זה פעמיים כל כך. K שווה 2. אז מה יש לי כאן? מה יש לי כאן? יש לי את זה כפול זה, ועוד זה כפול זה, ועוד זה כפול זה, וזה כפול זה. 4 איברים. נכון? כל אחד מהם הוא סכום של K טרם. פעם בחרתי את זה פה, פעם בחרתי את זה פה. זה יהיה D, אז זה יהיה לי D במינוס LX1 פחות LX1, אוקיי?
אבל סכום...
עכשיו יש לי עוד אחד, עוד סכום.
סכום לך כל השפה, אז הסכום לא יהיה רק את 2.
אתה אמרת שיש רק 2.
לא, יש 2 אותיות.
לא, זה לא 2 אותיות, זה 2 איברים בשפה. זה 2 מילים. הסכום הוא על X. אז אתה אמרת יש רק 2, יש 2 תמשיך, כן? כמה שיש. עכשיו, כל אחד מהאיברים פה הוא לבחור משהו פה, משהו פה, משהו פה, משהו. נכון. ולכן אני בחרתי משהו באיבר הראשון, ועוד משהו באיבר השני, וסיכמתי על כל האפשרויות לבחור אותם. אז בדיוק, מה יש לי? יש לי זה כפול זה, ועוד את זה כפול זה, אז לכן על כל 4 קומבינציות. זה סכום על כל קומבינציה. יש לי K איברים, ולכן יש לי K פעמים, K איברים שונים, כי אני חזקה את הכלי.
has to be smaller than 1, or else it would disobey this rule. If it's larger than 1, it would divert.
Okay.
If it's an exponential.
Ah, okay.
I am very tired. And I think it doesn't working.
等一下，其实我觉得他这边的铺符我后面慢慢跟上，但是我就觉得这个事情有点奇怪，就是比如说你把这个数sorry.
Sure, yeah. You can Chinese I don't understand, but
yeah,
getting better and better.
Just move this to here. It's clear to see. I mean.
No, I don't know. You can sum this anyway.
No, yeah.
Yeah.
Just move this to here, so I can
Okay,
have
well,
always
let's see the
Yes.
prefix code, right?
Right.
So
No, it's always prefix, and this is a prefix to
Yeah. But I mean just.
You want to change the code? Okay.
Just move this
Yes,
to here.
yes, you can.
Yeah. So
this will be monotonic. Yeah. Okay. Fine.
Yeah, so it's like so you can easily to see this, right? And so suppose that I have a K okay, I have a D alphabet. I have a D alphabet, so at least I need T node, right? T lead left, right?
This is your exercise. I don't want to do it yourself. Do it now, but exactly this is the kind of
Yeah.
I wanted to prove.
So it's just 2 minus 1 plus 2 minus 2 plus until 2 minus 3 minus 1 plus 2 minus 3 minus 1, right?
Yeah, at the end I can continue it forever.
Yeah.
This will be just the sum of all the
Yeah.
parts.
So it's 1, right?
Yeah.
So
So this is always 1 for any tree.
Yeah.
That's what I added.
Yeah. So if this is efficient,
If it's sufficient, all the leaves are used.
Yeah. All the leaves are used, so it's 1. So
right.
if it's not efficient, so this number could increase.
I missed some of them.
Yeah. So this
and
increase.
then it will be less than 1.
It will be less than 1, right?
But it's still unique to the column.
Yeah.
It cannot be greater than 1 with a 3.
Yeah. So yeah.
Okay.
The thing was it's like this. If it's unique, so the maximum is 1. If it's not unique, it will be smaller than 1.
Right.
Yeah.
Okay. Yeah. Good. That's all correct. Yeah. So if you have any questions, more questions, these are good questions. I want to include everyone. Because I want to continue now with faster pace. Okay.
I mean, if we have a D alphabet, so like with and we assume that the code is sufficient, so it's like
so we talked a little bit about codes. We understand what are uniquely decodable codes. And now we want to connect them back to statistics and estimation and all those problems. Now, so the interesting question is, we're talking about data compression here. So I have something and I want to describe it in the shortest possible way. Okay. So let's say I want to compress text. So text are, so let's say that I want to compress text at the level of letters, which is stupid because usually this will not give me a very good compression. So in this case, I want to map, let's say, the letters in the alphabet or the words, let's say, just to make it more interesting. You know, there are a finite number of letters, but there's quite a large number of words. But if, let's say, I limit my length of the words to 20, which is even good for Welsh or I don't know what, or some very crazy languages, 20 is more or less the maximum number of letters in a word. Maybe in Chinese the different story is different, I don't understand, but I don't know. How many letters do you have? The same, so the same as the number of words, essentially. Yeah. So that's not exactly fair, but you know, it's a different game. But in alphabets which are finite, then okay. So let's say that I want to encode my English, and or something with finite alphabets, and then I want to encode them by bits because I want to store the book on my disk or something like this. I want to transfer it through the internet. So there are many good reasons to describe it in a short way. I want to pay less my internet provider or whatever. So that's the motivation, the basic and very clear motivation today from what you call data compression. I want to minimize the length of the description. Okay, so is this clear? I'm not sure exactly which part of the board is the most redundant one. Maybe this one. So the connection to data compression is usually stated in the following. I want to find a code which will minimize the expected code length. So I want a code, so I want to map X into some sort of code length, of code words, such that and this has, of course, a length function. And I want the code to be efficient, so I want to find what is the minimal expected length, which is essentially just the sum over all x's of the length of the code. So this is the expected length. And this is something we want to minimize, but still being uniquely decodable. So, I mean, so here, for example, it doesn't really make sense to do a worst case bound or something like this, because you're really, the idea is that you're going to use the code many times, and essentially the number of, so the expected may be not good enough, I want to somehow bound the variance, but you know that if I'm coding a lot of words or a lot of letters, eventually I'm going to converge to the expectation with small variance. So I don't really care at that point about the variance. How do you minimize the mean? So what can I say about this? So essentially I want a lower bound. And as you already know, or you should, or at least should be able to guess, the lower bound is going to be related to the entropy. So actually, we're going to show that this is bounded by the entropy with the log taken at the base d. So d is the size of the alphabet. So it's if I'm talking about bits, this is log 2. Yeah. So this is going to be the proof. I'm going to show you this is bounded by the entropy of the source. So this is interesting. I mean, the entropy was defined in some sense as a property of the statistical distribution. So it was a sum of x log d of p of x. And I'm saying that this is a bound on the expected length of any code, which is uniquely decodable. So actually, this is the first part of what we call Shannon's lossless coding. Shannon's lossless, which is at this point a bit strange, but we'll see lossy codes later on. So lossless coding theorem. So the theorem actually has two parts. This is a lower bound, and then that in some sense asymptotically it's a tight lower bound, which means I can always achieve find a code which asymptotically is getting as close as I want to this bound. So the entropy is a tight lower bound on the length of the expected length of code. And this is known as, sometimes they call it Shannon's first coding theorem, because there are others. Okay? So just before I give you the formal proof of this, you already know from the asymptotic equipartition property that something like this must be true. Because we know already that if we look at only at typical sequences, so typical sequences over my variable xn, we already showed that the probability of a typical sequence is essentially what? Was between 2 to the minus n age of x minus epsilon. This is always confusing, and 2 to the minus n age of x plus epsilon. So this is a smaller number. This is a larger number. Okay? So we showed this already for typical sequences. Remember this? This was essentially the asymptotic equipartition property. So from AEP, the asymptotic equipartition property of the entropy, we know that most sequences, 1 minus, for any epsilon, I can find an n large enough such that the probability 1 minus epsilon is sequence is typical. So most sequences, 1 minus epsilon probability over the sequences are typical. Okay? So this is a very casual way of saying something more rigorous, but you can always complete it yourself. Okay, so this means, so essentially, for this to be true, so this means that all of them are equally likely, and this means that, and I also know, of course, that the number of typical sequences is bounded by essentially 2 to the n age. Okay. So if this is the number of typical sequences. So it's bounded by this minus epsilon, plus epsilon. So this means that if I use a sequence of size 2 to the n bits, I have enough holes in my pigeonhole to put all my pigeons. If I use nh bits, sorry. Yeah. If I use, so if my code words are going to be nh plus epsilon, so I'm using slightly more than nh bits for my code, and this is of course this should be an integer number, so take it the integer larger than this. And yeah, if Lx, if Lx is about this, actually, yeah, about this means for any epsilon, right? Then there are 2 to the nh holes in my pigeonhole, and then I can put all my pigeons, which is this is the number. I have enough holes for all of them. But this means that I can encode all the typical sequences by nh bits plus epsilon. Okay, so that's a very rough argument, just using equipartition, that something of the order of nh for a sequence of n of length n should be enough, and then for a single one, if I average it divide by n, I get that the average length for a single letter is bounded by the entropy. So only from this very simple pigeonhole argument, you already see that something like this must be true. You simply assign exactly nh bits to all the typical sequences, and whatever you want for the non-typical sequences, but then you push them to to epsilon, to push the epsilon to be small enough, so most of the sequences are going to have NH codes. NH. Okay, so this is now I'm going to show you a slightly more tight proof of this. Yeah.
And here is the number of code words, or
This is the length of the code.
the
The length of the code. So.
N is the length of the.
Yeah. So this is the length of xn. Yeah, you're right. Right. So it's a length. Xn was typical. Yeah. In the typicality argument, I used n words. I need n to be large. So for large n, I can do it with this, which means that for on average, which is divided this by n, this will be just h. So yeah, this implies that 1 over n L of xn is of order h plus epsilon. Okay.
What would be n in the example that you showed on the left board? Because what would be n in the example?
No, it's not. It's not this n. Yeah, it's this n. It's exactly this n. This is the size of the size of the code word of an extension. No, it's actually n is k here. Yeah, right. I confuse you. This n is this k, but forget what I said here. This was just a construction for this proof.
No, about the example that you showed before to give intuition. What do you think is n here?
So n here I'm talking about a single letter code, and the code. So in this case, k is 1, and the size of the alphabet, the cardinality of x was 4. And there's no n. I mean, n, the largest code here is 4 or 3 or whatever.
It would be
the size, n in this case is bounded by 3 bits. Yeah. The length of the code. I know it's very confusing, but don't mix the symbols from one proof in another proof. This is never good. Symbols I use just to explain things in one context, and then I use the same symbols in different contexts. If you mix them, you're not going to get anywhere. And this is a very context-sensitive thing.
So here n is the number of letters in.
Sorry? Yeah.
Here n is the number of symbols.
Yeah, here n was the number of symbols, yeah, and n is the number of bits. No, n is not the number of symbols. N h is the number of symbols. N was the size of the extension. When I'm using a sequence of length, remember how this p of xn was this product of x1 up to xn, and n is large enough such that the typicality argument holds. So n is the size of the number of. So you see that if I encode very long sequences, then something like the entropy, it's actually the Shannon-Macmillan entropy, the one that is the limit of log of minus log 1 over n log p. So this entropy is actually this. I mean the limit that n goes to infinity of minus 1 over n log the probability of a long sequence. So this is this entropy.
If you want to call it, for example, ABC, then n would be 3. Right?
You're forcing me to say things which I don't want to say. This is an asymptotic statement, what I'm saying here. And I don't want to talk about one case, okay? This is true only for the large n limit, okay? Now I want to talk about the general proof. Okay, so I can erase all this nice construction, and don't confuse the symbols from one proof to another proof, because I'm going to run out of symbols very quickly. We always use x, but in different contexts it means different things. Or n or k or whatever. Okay. So now I simply want to write the length code, the code length. There's something. Somehow didn't write down the proof, but I have to reconstruct it somehow. Okay, never mind. So it's so let's write this difference: sum of px lx minus the entropy. And I'm going to I'm going to prove that this is non-negative. This is what I want, okay? So what is this? This is sum over x of px lx plus sum over x px log, let's make it log d of px, okay? Okay, so now, just for simplicity, so I'm going to write, I want to, you see what I want to do. I want to essentially write this sum as one thing. So instead of, I'm going to write it as sum over x of px, and then since you want to put everything in the log, I'll write instead of lx, I write what? Log of d to the x. Okay? So this is a log of d to the lx, which is kind of cheating, but it's all right. Plus px, actually I can write it as, yeah, okay, p of sum plus log of px, okay? So this begins to look familiar, especially if I now write it as sum over x, px, log of px over, so this is d, d to the minus lx. This is the same thing. Because I put this as a minus sign here and put it in the numerator. Okay? And but what is this? Okay, so let's say, well, just for simplicity, denote qx d to the minus lx is qx. So this is just a denote notation. So this is essentially sum over x px log px over qx with this notation. But what I know is that qx, I know that the sum of the qx is what? What I just proved. Yeah, I know that the sum of the qx is essentially sum of d to the minus lx, so this is bounded by 1. Okay, so this is less than the sum of all the x's px log of px qx divided by the sum of qx, which is just the Kraft normalization, because I added a negative number, a positive number, but this is greater than 0 because it's the DKL. So this is the D of P and Q, Q normalized. So essentially the only thing I did here, this was almost a KL divergence, okay? If Q was normalized, so if there is an equality in the Kraft inequality, this is precisely a KL divergence, and I know it's greater than 1. It's greater than 0.
But you have over there smaller than, then you will have larger than, and then...
It's bigger than,
Yeah. The sign.
You divide by what?
It's all right. Believe me, it's true.
Yeah, just, no, it's the opposite direction.
Yeah, sorry. Greater than this, yeah. But this is greater than 0. Yeah, sorry. But I use this. I use this. If this is not true, then I don't have my inequality. Okay, so you see miraculously that the Kraft inequality allows me to prove that the entropy. So essentially, what we proved is that the expected length per letter is greater than the entropy. Okay, that's what we proved. So in order to use the KL divergence, I need to normalize these numbers. In order to normalize the numbers, I add a log of a smaller than 1 number, which is adding and subtracting a negative number, and that's why the inequalities are right. I mean, check it. Okay? It's a bit confusing because it's too many times that it's a log of 1 over a small number, smaller than 1 number. Okay, so we proved in one direction. So that's already interesting. So the entropy is the shortest possible compression on average of my data. So if the entropy is 0, so for example, if the language didn't have infinitely many sentences, if the entropy of English, let's say, was not positive, then I couldn't generate infinitely many sentences. So the fact that I can actually generate infinitely many sentences in English is equivalent to the statement that the entropy of English is positive. Okay. So the question, what is the entropy of English? That's a slightly different question. It's a technical question, how to measure it. So we know what the entropy of the letters of English. This is very easy. Just take the distribution of letters and calculate the entropy. But that's obviously an upper bound on the entropy because they are not independent. So if I have a bound on the entropy. Actually, the entropy of English, what is it, is actually an interesting question. Shannon estimated it in his famous paper on the entropy of English to be something like 5 bits per letter, or 3 bits per word, or something like this. 3 bits per word on average, which means that on average, it's only 2 to the 3, which is about 8 possibilities on average for the next word. Now we know that the entropy of English is actually much lower. It's lower than 2 bits per word. But this means that there are actually dependencies, very long dependencies. The more structured the source is, the lower the entropy.
Do you always want to go into the lowest limit that we can, or is there some kind
No, the question is how much I can compress English. Okay.
Yes,
So this is essentially telling me how many bits per letter or per word you need on your disk if you compress it in the best possible way. And the entropy is going to give you the lowest possible compression, the best possible compression. Okay, so what's the other direction? So the other direction is going through extension, of course. So notice, by the way, that if this is true, when do we have equality? You already see when you have equality. So when do we have equality in the KL divergence? If the two distributions are equal. So we're going to have equality. Let me write it here. We're going to have equality. So equality, which means that L of x is going to be equal to h if this Q of x is P of x, or if P of x is d to the minus L of x. This is equality. And of course, and the sum of d to the minus Lx is 1. I need both of them. So which means that I have an efficient code. I use all the lifts. This is the equality in the Kraft inequality. And I have this equality. But what is this? This I can write as L of x is minus log of P of x. Okay, but that's strange. In general, this is not an integer number. Okay? So the best I can do is to take the ceiling, the largest integer, something which, with the ceiling. So it's the largest integer that's greater than log of P of x. Okay, so actually this particular code, so this is what we mean by this bracket is the ceiling. So this is an upper bound. Now, when is it going to be inequality? So for example, this particular case that I wrote here, if all the lengths are, this is d equal 2, and all the lengths are power of 2, which means that if the probabilities are exactly 1 over, if the probabilities are d to the minus L, in this case the probabilities should be half, quarter, and 8 and 8, okay? So, because these are the 1 over d to the L. So if the probabilities are exactly exactly this number, then and only then, by the way, the code is optimal. It actually achieves this lower bound. So if my probabilities, let's say P of A equal 1/2, and P of B equal 1/4, and so on, and P of C equal P of D equal 1/8, then I have exactly a perfect code. Okay? But this, of course, is a very special distribution. This distribution is known as the Dyer distribution. It's exactly, if all my alphabets are exactly powers of my symbol. Let's say this may be not true for 2, maybe it's 3 for 3, or it's 3 for some finite alphabet, and so on. But in this case, I can actually get an equality in the Shannon bound without doing anything. Okay? But notice also something very interesting in this case. If this is true, that P is d to the minus L, then the sequence of the code will look like what? So let's say now I encode my symbols. Let's say I code a sequence, A, B, D, D, C, whatever, something like this. So this will have a sequence, okay. 1, and then B, 1, 0, 0, 0, 0, 0, and then B is 1, 0, and D is whatever, 1, 1, 0, 1, 1, 1, 1, 1, 1, and this is 1, 1, 0. No, this is a sequence. Now, if my probability is exactly as I said, the probability of seeing A is exactly 1/2. Okay, so it's exactly 1/2 in this branch. The probability of seeing B is exactly 1/4, which is a random walk here, and then another 1/2 in this branch. So essentially, the probability of the sequence look like exactly random walk with equal probabilities on my tree. In other words, because a random walk with equal probabilities on my tree will generate the letters in exactly the right probability. So this tells something which is general and generally true and very important. Optimal compression of my sequence looks like a random sequence of bits or symbols. Completely random. So you can't distinguish this optimal string from a completely random coin flips in this case. So, and this is true in general. I mean, as long as there is structure in my code, I can still compress it. It's perfectly compressed where all the bits look completely random, what we call white, no structure. So you see that the optimal code in this case, it doesn't look very random. It's actually, okay, because A, B, D, D, C is not really a random sequence here. But this is just, in some sense, the converse of the typicality argument. So a perfectly compressed sequence looks like random strings, random bits. And this is true in general. I mean, so when this comes to an equality, it means this is essentially the probability of generating a sequence of length L randomly on my code, independently. Okay, so remember this is very important. I mean, as long as there is some structure, some non-randomness in my code, I can compress further. Once you cannot compress anymore, it looks completely random. So random code, and of course, if it looks completely random, all the probabilities of these sequences is precisely 2 to the minus L. They're all equal and they're all typical. This is actually bad news, because if you look at a perfectly encoded sequence, let's say someone is transmitting a sequence which is perfectly, it will look like noise to you. Totally random. This, by the way, was one of the motivations of Shannon. I mean, he was thinking about codes in the cryptographic sense. And he said, let's say I want actually to transmit a sequence. He was saying, I don't know, if there is a spy in Berlin who is using a Morse code to transmit something over a very noisy channel somewhere else, so you want to minimize the length of the transmission because you don't want to be detected. So you want to minimize the length of the transmission, and you also want to minimize the ability to decipher it. So if you compress to the minimum length and then actually encode it, I mean, then XOR it with another random sequence, it will look random, totally random, nothing, no structure is there.
But then it will be hard to tell.
No, okay. Then it will be sensitive to noise. You're right. That's the second part. That's exactly why the next theorem, or the next topic in information theory, is how to fix errors if there's noise in the channel. Yeah. But this was the motivation. The motivation is very, very clear. So you want to minimize the length of sequence, and by that you actually generated a random sequence. Now what is the proof of the other direction? So I showed you that if, in this very special case, that the probability is exactly d to the minus some integers, and then I don't need to do anything. But in general, this is not true. So we already see from here that maybe this is not such a bad idea. I can take the ceiling, but if log p is large enough, then the ceiling will be close enough because what you are using by the ceiling, rounding the log of p into an integer, minus log of p into an integer, is bad if there are very few, but if log of p is sufficiently large, then not so bad. So essentially, the idea of the other direction, so let's look at an extension. So I proved that the entropy is the lower bound, and I want to prove that it's a tight log. Okay, so let's look at an extension of my code. Okay, so an extension of my code, so again, I actually already proved it. So if I want now to prove an extension, I know that log of p, so this is just like saying, this by the way is like saying that log of p of x, or minus log of p of x, is between Lx and L plus 1. This is the same thing. I mean, this ceiling, this is what it means. So I'm rounding it to the next, I'm sorry, less or equal than and less than L1. So if this can be equal to Lx, then where Lx are integers. Okay, so this is again, if I can write log of d rounded between two different integers, then I'm fine. So the question is how tight I can make it. So this is the meaning of the ceiling. Yeah? I round it to the nearest possible. Sorry, yeah, it's actually this way. The nearest possible larger integer. Okay. So now look at the extension. So I know already that the extension. So I can find the code where this is greater than the length of the extension.
After rounding it, or?
No, so I do the same argument exactly, but this time I talk about an extension of the code. So I know that I can always find this is what we call a Shannon code. I know Shannon appears there all the time, so it's a bit confusing. Shannon's code. So essentially just find the closest possible integer. But now I do it not for x itself, but an extension of x. So it's the same argument again, plus 1. So I know that I can find a code which obeys this.
Technical, in the Shannon's code,
yeah.
The minus should be inside the otherwise you might get.
You're absolutely right. Yeah. And there should be a minus here. Yeah, you're absolutely right. First, I want it to be a positive number, and then you take it up above. Okay. So this is what it means. I can do this. Okay, but now I'm interested in the code per symbol. Remember the average code. So now I encoded a sequence. This is a sequence of n letters, of n objects, whatever, n objects, n x's, just as we did all the time. So I divide by n. I want to see the average per symbol. So dividing by n is just what we do all the time. Yeah. Is greater than L of xn over n. But this is just L of x. This is what I call the average L of x. Plus 1 over n. Okay. So what did I get?
Did you assume that n is large?
Yeah, not yet. But now I'm going to assume.
How can it be the expected value?
No, it's not yet. Okay, you're right. You're right. This is 1 over n. At this point, it's 1 over n, the length of the sequence. Okay? And the length. Okay, now I'm using exactly the same argument I used before. This is going to converge to what? When n is large? To the entropy. And this is going to converge to the average L. And this is going to converge to the average L. So I'm going to have that the average L is the entropy is greater than the average and less than the average L plus the 1 over n, but this 1 over n goes to 0. Okay, so I got a sandwich. I got that the entropy is as close as I want to the average L. Up to 1 over n, but 1 over n goes to 0. So in other words, this is proving that the bound is tight, which I can get as close as I want with the average L to the entropy. Okay, so that's proving it. It's not just the lower bound, it's a tight lower bound. I can get as close as I want up to 1 over n. All right, so this is interesting. But, okay, so this Shannon code is something interesting, actually, this Shannon code. So remember, I want to go back to our questions. You remember the 20-question game and the coin weighting and so on. I mean, all these type of questions, or actually in general, it's measurement design, it's experimental design. How do I design the minimum number of questions that I want to ask about a variable in order to recover it? And now you see, or you begin to see, that this is essentially equivalent to designing a code. So let's say that I want to ask binary questions about, the 20-question game, you remember? Yeah, you all remember, this is important. So essentially what I did there was looking for a way, so you got this bound, the entropy of the original uncertainty, divided by the uncertainty I can remove with one measurement. But now the one measurement is turning into a branch in this tree. So remember that in general I can write not necessarily a prefix code, but I can always find a prefix code for my variable. That's because I can always find, for any Kraft inequality, for any length function which obeys the Kraft inequality, I can find a prefix code or a tree. But now you can interpret this tree as a set of questions. Okay, so this is the first question, and this is the second question, this is the third question, and so on. So essentially, if I want to solve now, let's say the 20 question, it's rather easy. Divide by half the numbers. You do a halving algorithm. Since you can compare, since the numbers are sorted on a line, there's always a half, more or less halving the number, and this gives you essentially an optimal strategy, because it gives you essentially one bit. So again, it's the converse of what I said before. The fact that these are random bits for an optimal code means that my questions are optimal in the sense that the probability of the answer is maximal entropy. It's most uncertain. I maximize the uncertainty of the answers. So a code is essentially, an optimal code is an optimal questionnaire. It's an optimal set of questions on my variable. Okay, so now go to the 12 coin problem, which actually you're supposed to think about in your exercise, but we lost so many exercises that it's already irrelevant, but I still want you to think about it. So how do you solve it? So you have to design a code, a binary, a trinary code, in this case, because there was a balance scale there. So you need to design a trinary optimal code for your variables. And this will actually give you the optimal way of weighing. And so the question is, how do you design an optimal code? And it's an algorithm. So Shannon, it's actually sometimes called Shannon-Fano code. Shannon and Fano, they're two people. Shannon-Fano codes. So they're essentially this greedy encoding. I mean, so it's essentially this. I mean, try to maximize the entropy of the next bit. So take the most divide it such that this will be maximal entropy. But this turned out to be not the optimal way of doing it. So essentially, you see here that I'm missing 1 in my code. The question is, do I really need to, and it's only going to go to 0 when I use extensions. Then this 1 is turned into 1 over n. But the question is really, this is the best you can do, losing up to 1 bit. And this is the best I can do for a single letter code. So the question is, no, there's actually a slightly better algorithm, which is interesting because it's a very simple algorithm. It's called the Huffman Code.
The
Shannon code in some sense greedy code. I mean, so whenever you need to encode the next symbol, you look for the maximum entry partition of your data. This is what we did with the questionnaires, for example. But it turns out this is not the best you can do. So how many of you learned about the Huffman Code somewhere? All of you, most of you. Okay, that's easy. But I'm sure you learned about it in slightly different context, maybe. Huffman Code. So there's an algorithm which was not designed by Shannon. So Shannon actually asked, here is the best I can do, take essentially this ceiling or this upper integer, which means that at every point in my coding, I maximize the entropy of the next question. But sometimes this may lead to bad questions. So it turns out that actually the optimal way of doing it, that this is something much more general, which is true for many other type of problems, is essentially using the principle of dynamic programming. I mean, so how many of you heard about dynamic programming? Of course, all the computer scientists, but none of the others. So dynamic programming is in some sense an optimal way of solving a sequential problem like this. And I'm not going to prove anything about dynamic programming. I'm not going to ask anything about dynamic programming. It's not part of this course, but you should all know this principle. So essentially, if you want to optimize, let's say, a sequence of states, so usually the best way of doing it is actually going backward. I mean, start from the end, and then say, okay, let's say what happens one step before the end. And in some sense, going backward is giving you a better algorithm. So Huffman coding is it's actually a special case of dynamic programming. I mean, most people don't really tell you that, because it's not, I don't know why, but it's quite easy to see it's a special case of dynamic programming. And the idea is, let's say that you have a finite, so let's say that my letters are x1 to xk, or some finite letters, and they have probabilities p1 to pk. Okay? So I know the probabilities to start with. Of course, this is a very strong assumption in some cases. We'll talk about coding without knowing the probabilities next, but not today. So what Huffman is telling, essentially, let's say that I sort them. I sort them such that this is the largest number, this is the smallest number. Okay, I can always do this, of course. So then, yes, I sort the probability of the variables. And then the Huffman coding is telling me, you know what you really want, I mean, if you think about it in terms of entropy, in order for the code to be efficient, you don't want to get to too deep inside the tree if you don't have to. I mean, so these things which are rare should be down. That's what this is telling us, because the probability should go like 2 to the minus d, minus L of x. So the lengths of the small probabilities should be larger, and the high probability should be shorter. This is just a very simple principle. I mean, things which are frequent should get short code, and which are rare should get long code. This is the same principle again and again. Okay. So this is already written there. Yeah. So the rare events or the rare objects should get longer code.
So